Okay, so how is your preparation is going on? Good?
Good, sir.
You know you guys are taking your exam tomorrow, right?
Yes, sir.
Yes, sir.
Good. Wow, nice dog, Raji. Good. John, are you looking fresh today?
Excuse me, sir?
Are you looking fresh? Little sleepy?
A little sleepy, but I'm good. I'm good.
You're good. Sorry about all these timings, but you know, sometimes you have to follow this. I'm sorry.
I'm getting, you know, got to do what you got to do.
Yeah, just last 4 days, and you're done.
Exactly. So I actually had some questions about this week, sir. How does it all work out? Because we have our...
I think whatever you raised, that's a good question, John, actually, because what I think that after your exam, it's a big responsibility on you guys.
It's tough, yeah.
Try to go through all your exams, all 4 exams, and whatever you have not done correctly, try to keep those things separate. Try to get the answers from our videos or our class notes or what, etc. And even though if you're not getting something, please let me know. Keep those things aside and we will discuss those things on Wednesday. Right? So please try to utilize Wednesday time. If you are coming over here without doing anything, probably that's not the way to do the review session. And I can't answer your question.
Would you recommend the tests as the main study guide, or would you recommend the practice tests as the main study guide?
Again, there's a good question. See, if you are looking for, suppose, the B grade or like this, then I think whatever 4 tests I give it to you, you can go through those type of tests. I mean, say those examples, and very similar kind of examples will be there in the final. But if you're for suppose A, like A plus, something like that, in that case, you need to go through all the examples I give it to you in the practice test. Now, examples will not be exactly similar to the practice test. Example will be different. Different, I mean to say that I'm not going to change the pattern, but most likely the numbers will be different. So if you think that I can memorize the answer and I can write it down, no, you will be probably going to mess up your exam. So don't do this thing. Alexis Davis, we are discussing very important thing. Please keep yourself on our side, please, please, please. A request. Okay. So that's the thing, guys. But yeah, and that's why I told you that please try to go through all the stuff without making, without leaving a single thing. If you are not understanding some of the things, some stuff, some lines, again, you can ask me, we'll discuss over here. But don't try to memorize any of the things. Otherwise, you know you are going to mess up your exam. So don't do this thing. Please understand each and everything. So if somebody changes, I'm sorry. If somebody changes the numbers, okay, in that case, you don't face any problem.
Okay, thank you, sir.
Yeah, but it will be very parallel, very parallel.
All right, yes, sir. Thank you very much.
Yeah. Like I can give you some hint. Of course, I want to discuss this thing day after tomorrow on Wednesday in the review session, but let me give you some hints. Suppose for left-hand side, right-hand side rule, right? Riemann sum. In Riemann sum, I may give you something, some figure, and I will not ask you to go through complete left-hand side rule or right-hand side rule, but I will give you some figure and you need to use that figure to fix your left-hand rule and right-hand rule. So that is way easier than what we have gone through in the, but that's what I'm thinking. So right now, there is just a kind of hint you can say. Don't say that exactly same thing I'm going to ask you. Second thing, suppose work done. Okay, work done problem is really easy, but suppose fluid force. So in fluid force problem, I'm going to give you one figure. One figure, I mean to say that, you know, we have different type of figure, maybe rectangle, maybe square, maybe triangle, reverse triangle, rhombus, something like that.
Yes, sir.
So I will provide you figures, the numbers, right? So that it would be easier for you to solve that example, to fix your x-axis, y-axis, and try to use the formula for the vertical force of fluid flow, right? So figure will be provided to you. In last part, or maybe in the middle of the exam, you may find I'm not going to maintain this sequence of all the chapters. No, you may get suppose series and sequence examples in the middle of the exam.
Okay.
16 questions out of 16, you may get 10th number 10 that is based on series and sequence. Don't think that everything will be in sequence. Why? Because your first question, that will be the objective question. Objective question, that means it's a multiple choice. Multiple choice, that means I will ask you one question and 4 choices are there, 3 to 4 choices are there. You need to pick the right one. Are you getting?
Sir, that makes sense.
Right?
Yes, sir.
Good. So first question will be like this, and that's why we are going to cover starting from beginning to the end, everything in the multiple choice. And then after again, we'll start from the beginning for the long questions, right? Descriptive parts. So please keep in mind these things. And again, in series and sequence, I'm going to provide you, I will give you one example, some space, second example, some space, third example, some space. You need to write it down in the same space. Don't think that you can write down in a separate piece of paper and that is allowed. No, in the final, that is not allowed. That is, let me let you know this thing in advance. If you don't have printer, try to arrange it. But you are not allowed to write anything in a separate piece of paper. You have to use the same exam which I'm going to provide you. So please make sure that your printer, everything is working properly before the exam, before a day of the exam, I would say. Yeah, because at the time of the exam, suppose somebody says that my printer is not working, blah, blah, blah. I don't want to listen any kind of excuses, guys, because owner code says that whatever the exam we are going to provide you, you need to use the same exam. So in the internal, the ball was in our court. So that's why I took some liberty and I allowed you to use some separate piece of paper, some of you. Those, but for the final, I'm sorry guys, but please arrange something. You can borrow a printer for a day or for a couple hours like this from your friend, whatever you, that's your part that you need to manage. But I want complete exam, whatever I'm going to post on Canvas, exactly same thing you need to use, right? Don't use separate piece of paper, that is not allowed in the final. Those who are not here, I think Cooper is not here, right? And who is the second one? These 2 guys are not here.
Yes, sir. I just connected.
Cooper, okay, please try to come in time. I spoke
Yes, sir.
3 times. Okay, so all you guys, those who, I think only one person right now. Anyway, so yeah, that is his loss. So please try to follow all these instructions. Don't say that we did not discuss any of these things before the final. Don't say like this. If you have any questions, please keep all your questions related to our study. I don't want just the questions based on our study. I mean to say our chapters. No, you can ask me some other questions like whatever John raised the question. You can ask me this type of questions too. And I would be glad to answer your questions, your doubts. Right, guys? So I think that is good. But in the final, please make sure. And again, owner code says that I can't provide you any extra time to resubmit, to submit your final on Canvas. Yes, final means, I'm sorry guys, in the internal exam, I gave you some extra time so that you can fix your problems if somebody needed some more time. But in the final, I'm sorry guys, once you are given 3 hours, exactly 8 a.m., whatever time is fixed, exam will start and it has to end at 11 a.m. And 10 minutes I can give you just to resubmit because that's online teaching. So just, I can give you 10 minutes, but I can't give you more than 10 minutes. So please make sure that all your technologies, everything, submission on Canvas, your printer, everything works well, right? Before you start your exam. Please guys, that's a request, please. Because I don't want to hear any kind of thing. Simon, are you here? Simon. What he's doing?
Yes, sir, I'm here.
Why are you late always?
Sorry, sir.
Okay, fine. I hope you got my email yesterday, right?
Yes, I saw it. Thank you.
No problem. Please be particular, guys, right? Be particular. Yeah, so all are present. That sounds good. So, yeah, so at the time of the exam, I just want all you guys to come to the Zoom online meeting just before 5 minutes, at least 5 minutes before the exam. Yeah, don't think that our exam starts at 8. That means you can sign up at 8 a.m. No, you have to sign up at least for 5-10 minutes before. So if you have some last minute doubts, if you want some of the hints, some of the help, at least I can help you out. Am I right, guys?
Sir,
Yes.
our exam isn't at 8 a.m.
Our exam is at 2 p.m. I'm sorry.
Yes, sir. It's at 2
p.m. I'm going to say, yeah, I'm sorry. Yeah, 2 p.m. I'm going to say that you need to come online. You need to come to the online around 1. you like this, and I will also be here just to
Yes,
help
sir. I
you
just
out.
wanted to make sure we
Yeah,
were
so
on the
timing,
same.
yeah, that was just the example. 8 a.m. That's just the example. I know that our exam starts at 2 p.m. 2 p.m. or 1 p.m. I think it is 1, not
Two.
no, it's 1. Make sure. I got the message yesterday. It's 1 p.m. It's 1 to 4. Cooper, make sure.
Yes, sir. I'm making sure right now.
Yeah, because there is no extra time for anybody. If you are missing that time, that is your loss, guys. Please don't blame me. And I'm not fixing that time. Just check the website. Don't ask me. Don't say that you told us this time. No, I'm not telling you anything. I'm not telling you anything. You need to check your website, VMI website, and whatever time they have mentioned, you have to follow that time. So please, guys. Cooper, am I right? I think it is 1 p.m.
Yes, sir. It is 1 p.m. to 4 p.m.
1 to 4, yes. So please make sure, guys. Yeah, somebody told me yesterday, no, last week, that our exam starts at 2, and I double checked yesterday, and I got surprised. I think this is the right time. And
yes, sir. They're probably just used to the
question, yeah, so
VMI
all
where
of you
it's at
guys,
2.
right, guys. You know, sometimes you are well prepared, and because just you miss the time, and that's why you're losing your grades and exam, all these things, you are messing up your exam. Don't do this thing, please, guys. Double
Yes,
check.
sir.
And if I am not online, just send the email to John, and he will send the message to me, and immediately in 5 minutes, I promise you guys, I'll be online. I promise you. Yeah, just send a message to John, and immediately I'll be online. Right, guys? So please do this thing. And 2 p.m., that means I think that time is really good for John. He will have some good sleep night, right?
It'll be perfect. Yes, sir.
Good. Okay, guys, so let's continue, right? Yeah, lots of time we just spent just 15 minutes here we spent for the instruction, but I think that is equally important. And now we are going to share the screen, and that is important for all of us too, because you know sometimes yeah, one has to be very particular in time, because if you are particular in time, that means, trust me, guys, you already you have finished the one step. You are one step ahead in your life. Once you are in time, once you are time bounded, once you know how to respect time, that means already one step is covered in your progress. Yeah. So please keep in mind this thing. Time makes a big difference. Big difference. Respect. If you respect time, trust me, guys, time will respect you in future. That is my slogan. Yeah. I used to tell this thing so many times to my students that those who don't respect time, time never respects them. No, never. But if you respect time right now, nowadays, and if you try to finish your graduation with good scores, good GPA, you're going to get good job, and time will respect you in future. So respect time and take the reward. Okay, guys. So last week we did the infinite series, and I just gave you the examples. First of all, the definition of the sequence. That series sequence is nothing but a function whose domain is a set of natural number, and sequence is always identified by its codomain. And then after I gave you several examples, number of examples like this, and we went over the different terms of the sequence A1, A2, A3, and like this. And then after I gave you 3 different examples. Then after I gave you the limit definition of the sequence. And this is a geometrical picture of a limit definition. And then after a very standard example, we use this example in our indeterminate form too, right? An equal to 1 plus 1 by n to the power n. In indeterminate form, we just use this one as our fx or some that is equal to some function, right? Function of x, 1 plus 1 over x to the power x. Here it is sequence or terms are A1, A2, A3. So let me use number n. N belongs to capital N, a set of natural number. And we figure it out that sequence is convergent if limit is finite real number. And then after some properties of sequence, and then after we went over the monotonicity and the boundedness of the sequence. There is another way of approaching whether your sequence is convergent or divergent. If it is monotonically either increasing or decreasing, but if it is bounded above as well as bounded below, that is boundedness. So monotonicity plus boundedness gives you again the convergence. Your definition of the limit of the sequence and your definition of this monotonicity and the boundedness must coincide each other. That means once you are getting the monotonicity convergent by monotonicity and boundedness, that means after applying limit you must get the same answer and the vice versa. So please make sure this thing. And then after I told you that a sequence is convergent, that does not mean the series is convergent, but the series is convergent, that is immediately imply that the sequence is convergent. Please keep in mind this thing, because sequence is nothing but the term, series is nothing but the terms of the sequence. So one term, suppose one term is convergent, that does not imply that whole term, sum of all terms, all n terms will be converged. So please keep in mind this thing. And then after, so we went over this example. Then after we went over finding the nth term of the sequence, because without finding the nth term, you cannot pass the limit. So I just gave you first 4 or 5 terms, and then after we fixed the n terms using our algebra scale 2, 4, 5, 8. So it's, see like this, denominator is 1, 3, 5, difference is 2. So arithmetic progression, here it is 2 to the power something, right? And this way we finish this one. And then after just monotonicity boundedness definition is there. And yeah, 1 over n, you can see if you pass the limit as n tends to infinity, so 1 over infinity is 0. So n approaches to 0 from right side, right? Because it is 1, 1 by 2, 1 by 3 like this, approaches to 0. That means sequence is convergent. The sequence is convergent. It is monotonically decreasing because 1, 1 by 2, 1 by 3, every time the terms are decreasing, each term is numerically less than the preceding term. So that's why it is monotonically decreasing sequence. And this sequence, if you take A1, A2, A3 up to AN like this, some A1, A2, A3 up to A7, A5, A7, A10 up to A10, suppose. That means you can see that my highest number is 1 and my sequence is not going to cross 0. That means it is bounded below by 0 and bounded above by 1. So it is monotonically decreasing and bounded. That means it is convergent. So both the ways you can check this thing. That's what we discussed last time. And then after we started infinite series is nothing but the sum of the sequence. I told you, then first we are going to find the partial sum. Partial sum, that is nothing but the sum of first n terms. And once you have first n term, then after you are allowed to use the limit. So I would like to give the name Sn. Whenever I write symbol, I use the symbol S or S of n, it is to be understood that we are looking for the partial sum. So Sn is the partial sum, summation of A1, A2 up to An. So A1 plus A2 up to An, sum of first n term. It is the infinite series, but we have to fix one n, and then after we allow n tends to infinity, right, to get the convergence or the divergence of the sequence. And if you pass the limit and Sn tends to some real number S, it is series is convergent. If it tends to either plus or minus infinity, series is divergent. Series is divergent. And then after we went over a few of the exams, right now I'm giving you the review session, guys. Then after we went over a few of the examples, look at over here, few of the examples, 1 over 2 to the power n, right? And I just applied the definition that what is my first term, my second term, third term, and then after I found my nth term, and then after I pass the limit, and that is equal to 1, fixed real number, my S equal to 1, that means this series is convergent. Actually, this is a geometrical progression, that because it is summation A r to the power n, r equal to 1 by 2. R equal to 1 by 2, and 1 by 2 is less than 1, so series is convergent. Right now, when I started this example, at that time, we did not have any kind of geometrical test. I did not teach you any geometrical test, and that's why I apply just the definition over here and try to show how the sequence is convergent. But actually, you can use over here the geometrical progression, summation is there, an is simply 1 over here, summation a is 1 over here, r to the power n. So n, I would like to write out. So it is 1 by 2, r equal to 1 by 2. And geometrical progression definition says that when r equal to absolute value of r is less than 1, series is convergent, otherwise it is divergent. So here it is 1 by 2 is less than 1 naturally. So that's why by geometrical series, right, the series is convergent. Okay, and then after we talk about the telescopic series, so whenever we have this type of series at that time, you can just plug different values of n equal to 1, 2, 3, 4, 5, 6, 7 like this, up to n as well as the previous term, n minus 1th term. And you can see most of the terms will get cancelled out, and you will be added up with either couple terms or first and last term, or first, second, and last term, not more than 3 terms maximum, right? So that will be your n, because you ended up at nth term, and that's why this is your partial sum, and then pass the limit. So most likely telescopic series will be convergent, most likely. Okay, oscillating series always divergent, sequence of n term constant series is always divergent, because for n equal to 1 to infinity, you're going to get constant terms, and that tends to infinity, so always divergent. Very nice example, 2 over 2n 4n square minus 1, whenever we have towards the right now, just pay attention over here. If you have some questions in your mind, keep those questions aside, and we will discuss those questions day after tomorrow in the review session. But don't send the email to me right now. Simon, please, I don't want you to divert your mind, please.
Yes, sir.
Just pay attention over here right now. Okay, now an equal to 2 over 4n square minus 1, right? So whenever you have a product of two numbers in the denominator, so many times I told you that means first we have to go through the method of partial fraction, so that we can write the denominator in a linear term, either plus or minus term like this. So that is the purpose of writing or using method of partial fraction, so that we can write this denominator in two separate terms. Once you have two separate terms, then after you can find the partial sum, n equal to 1 to 3 like this, up to n, and n minus 1 term, or most likely you're going to get the telescopic series, terms will get cancelled out, and that's why finally you can pass the limit and sequence is convergent or like this. So most likely, not all, but most likely the telescopic series will converge. That's a convergent series. Geometric series, this is the definition, summation ar to the power n, that is a plus ar to the power and ar square, ar cube like this. And if this r is less than 1, r is less than 1, look at here, strictly less than 1. If r equal to 1, that won't work. R equal to 1 is divergent. But r is strictly less than 1, 1 by 2, 1 by 3, 1 by 5, 1 by 8, 1 by 1000, 1 by trillion, right? Strictly less than 1, then it is convergent, otherwise it is divergent. And some of the geometric series is given by a over 1 minus r. A is the first term, r is the ratio, right? Because ratio, see why this is called the geometric series. Last time we discussed about the arithmetic progression, because arithmetic progression, that means terms between, difference between two terms are same. So 1, 3, 5, 7, you can say every time we have a difference of 2. So that's why it is called the arithmetic progression. But geometric series, that means suppose ar to the power 1 divided by a, right? So ar, pick the second term, divide by this first term, means you are getting r. Take the third term, ar square, divided by previous term, ar, again you are going to get r. Pick the fourth term, ar cube, divide by this previous term, ar square, again you are going to get r. That means every time the ratio is r. And that's why it is called the geometric series, right? So whenever the ratio between two, not the difference, but the ratio between two ratio between two terms, that is same. Ratio between two terms, that is same. In that case, you can say, you look at over here, you can say there is a geometrical progression. Ratio between two consecutive terms must be same for the geometrical progression. And again, I took the same example, 1 over 2 to the power n. Previously, when I started the infinite series, I used the definition, but now you have this geometric test. So use this geometric test, and immediately you can say that, see, 1 over 2 to the power n can be written as 1 by 2 to the power n. 1 is your a, r is 1 by 2, a is 1, r is 1 by 2 is less than 1, series is convergent. But you have to mention here your, if you don't mention, guys, please pay attention. I'm going to teach you 4 or 5 tests, and you have to mention, when I ask you this example in the exam, at that time, you have to mention your test, that which test is applicable or which test you have used to figure it out whether this series is convergent or divergent. And if you don't write test, that means again you will be losing your points. Guys, please, I'm giving you all the instructions, and if you want to follow this one or not, that's your choice. But I need to cut your points if you're not following me. Okay, so
Sir,
I'm getting some noise here. Yes, John.
For the tests, would it be, would you just have to continually use like the p-test? Because for a lot of the examples, the majority of them are either p-test, comparison, or geometric.
No. That's the wrong interpretation.
Not specifically for this example. I'm talking about overall.
Overall, the p-test, no, you are going to get hardly 1 or 2 examples, not more than 2 based on p-test. So don't think that you can use p-test for most of the series. No, it's not going to work.
Oh yeah, I completely understand. I was just wondering if you had like a list of the tests that we would need to be able to use, because I know I can like.
I don't have a list of the tests, but I think you guys can prepare one list and just send it to me, and I will approve it, and I will allow you to use that one in the exam. But one more thing. No, one more thing, guys. I think the list is already there in your formula sheet. First formula sheet I give it to you. List.
Oh, okay, yes, sir.
Yeah,
Thank
so
you
just
very
make
much.
sure. I think last part of the formula sheet contains the whole list.
All right, thank you very much, sir.
Good to go. Yep. Good, guys. Suppose I have another example, 3 over 9. And here, if you want to write sum A equal to 1, look at over here, A equal to 1. So A is 1 and R is a ratio that is equal to half. So 1 over 1 by 2, that is equal to 2. So 2 is the sum for this geometric series. Some same 3 to the power, and some people write this 3 out and then they consider this A equal to 1. That sounds good. And finally, they multiply it by 3. Or you can consider A equal to 3 and then R equal to 1 by 2. Both ways you will get the same answer, right? Now, few more properties that suppose an converges to some number A, Bn converges to some number B, series an is A, Bn is B. Then if you multiply some constant with your convergent series C, by multiplying some real number, some constant, your convergent nature or the divergent nature of the series won't be affected. That means suppose your series is already convergent, and if you're multiplying that series by some constant number, suppose 1000, C equal to 1000, again that series will remain convergent. If your series is divergent, if you're multiplied by some big number, suppose trillion, again your series will be divergent. Or suppose you're multiplied by 5, it won't affect. So multiplying your series by some constant won't affect your convergence or divergence concept. Suppose your first series is convergent, your second series is convergent. Suppose first series converges to 100, second series converges to 300. That means that sum will converge to 400. Means again a real number. That means sum of two convergent series will again a convergent, and difference of two convergent series will again a convergent. Okay, and sum of two series can be written in the form of suppose series of an plus, because infinite series is linear in addition and subtraction. So please keep in mind this thing. Again, you are going to get the numbers a and b, and again there's a fixed real number, so it is convergent. Most important test is nth term test. We also already discussed this nth term test also last time, that summation, suppose your series is convergent. Look at here. No, I think we did not discuss the nth term test. We discussed P series test, right? 1 over n to the power P. That is this one, 1 over n to the power P. 1 over n to the power P is convergent if your P, look at here guys, power P is greater than 1. This is kind of reverse situation than the geometric series. In geometric series, your ratio was R equal to less than 1. Here it is strictly greater than 1, P equal to summation 1 over n to the power P. Suppose I give you summation 1 over n. So summation 1 over n means n to the power 1. 1 lies over here. That means your summation 1 over n is divergent. And that's what we have seen previously. Summation 1 over n is divergent, right? Sequence an is divergent. Series an equal to 1 over n, divergent. But suppose I take n equal to 2, 1 over n square. So square means 2. And 1 is greater than P, 2 is greater than 1, 2 is greater than 1, that means it is convergent. So 1 over n square, 1 over n cube, 1 over n to the power 4, 5, 6, whatever number greater than 1, for all that terms, 1 over n to the power P is convergent. Look at over here, I gave you some numbers over here, right? It is suppose you have 1 over 5 n cube, so take 1 over 5th out, and summation 1 over n cube. P series test says that you have to mention over here in the bracket. By P series test, this one is convergent, like this. So after doing this P series test, now I would like to start the nth term test, because we are using this P series test in our nth term test. Our P series test says that, nth term test says that, nth term test, very important test, you will be getting one question based on this nth term test. And you have to figure it out that which test is applicable for your exam, guys, for your example, sorry. Yeah, you are the right person to judge which test is applicable, whether it is geometric test, P series test, nth term test, whatever it may be, right? Excuse me. Sorry. Okay, guys. Now, nth term test. Nth term test says that if your series is convergent, look at here, if your series is convergent, then nth term always tends to 0. Nth term always tends to 0. If your series is convergent, your nth term always tends to 0. Suppose, let me take one series, suppose 1 over n square. Nth term means you are talking about the sequence. When series is convergent, please pay attention, all of you. If series is convergent, its nth term means we are talking about just one nth term sequence. Nth term of that series, one sequence, that is always convergent. One nth term of that series is always convergent. That means an converges to 0 as n tends to infinity. But the converse is not true. Nth term tends to 0. That does not mean that series is convergent. Very standard example. So reverse part is not true, please guys. Very standard example is 1 over n. Series 1 over n by p series test. See, 1 over n means n to the power 1. N to the power 1 lies over here, so series is divergent. So summation 1 over n. So if you take limit n tends to, I'm sorry. Yeah, so this one is divergent. But if you take series limit n tends to infinity, 1 over infinity is 0, means n term tends to 0. Look at here, n term tends to 0. But because p series test 1 over n to the power 1, p series test, it is divergent. Right, guys? It is divergent. That means the converse is not true. This is the example for which my nth term tends to 0. Nth term of the series tends to 0, even though my series is not convergent. It is divergent. So converse is not true. Just one part is true, just one side. It is if series is convergent, n term tends to 0. But the most important thing is the negation of this result is highly useful. Negation of the result means, here guys, Kupar, John, here. Negation of the result, Soto, Thomas William, please, Williamson. Negation of the result is if nth term does not tend to 0. Look at my cursor. Limit n tends to infinity, an is not equal to 0, does not tend to 0, tend to some number, 2, 3, 5, 1 by 2, what it may be, negative 1 by 7, what it may be. If n term does not tend to 0, but some real number, your series is divergent. So series is convergent, n term tends to 0. Converse is not true, that means n term, converse is not true. That means there are some series for which n term tends to 0, but the series is not convergent. But the negation of this result means, what is the negative part? When nth term does not tend to 0, series is always divergent. Nth term, this is called the negation of nth term. If limit n tends to infinity, an not equal to 0, series is always, this is infinity. Series is always divergent. Always divergent. Right? Series is always divergent. Okay. As per example, don't take this example because this is the example based on the comparison test, and comparison test right now that is not in our syllabus. It was in our syllabus previously, but not right now. And you're going to learn this comparison test and Cauchy and through test and alternative series, all these things in your advanced calculus course 301. But right now, don't pay attention on this box. That's why I put the box, and that's why I write down don't blue. But here, suppose I take summation, suppose I take summation 2 to the power n. Summation 2 to the power n. So if you pass the limit n tends to infinity of an 2 to the power n is infinity, 2 to the power infinity is infinity, because 2 square, 2 cube, 2 4, 2 5, every time your number is rapidly increasing. So that's why it is infinity. Once it is infinity, right? So nth term does not tend to 0 because it is infinity. See, limit n tends to infinity, an is not equal to 0. An is not equal to 0. That means this side, this one. So naturally, I can say by the negation of nth term test, you can say that series is divergent. See, like this. So I repeat, people are getting confused in this nth term test, guys. So please be careful. I repeat, it says that series is convergent, then nth term always tends to 0. but the converse is not true. But if n term does not tend to 0, series is always divergent. So we are using this part. N term does not tend to 0. My n term here does not tend to 0. My series is divergent. My series is divergent. Right, guys? My series is divergent. Okay. Another example, n square over n square plus 1. Let me take n square out. My nth term is n square over n square plus 1. Let me take n square out, n square out. So 1 over 1 plus n square. If I pass the limit as n tends to infinity, 1 over infinity is 0. So 1 over 1 plus 1, that is equal to 1. But 1 is not 0. 1 is different from 0. So nth term does not tend to 0. It has to tend to 0. But n term does not tend to 0. Some other number than 0. That means by negation of nth term test, series is divergent. It is divergent. Right, guys? Good. And then after we go through one more test, and that is called the alternating series. Alternating series. Alternating series means terms are alternatively positive and negative, or negative and positive, but one positive, one negative, one positive, one negative, one positive, or starts with one negative, then positive, negative, positive, negative, positive, like this. So whenever terms are alternatively positive and negative, at that time that series is called the alternative series. And whenever you alternative series, just blindly apply Leibniz rule. So first of all, what we mean by Leibniz rule? Whenever you have alternative series, at that time, if you take the absolute value, that means you are removing this negative sign, negative 1 to the power n, and the absolute value, that will make it that will make it positive. So an equal to absolute value 1 by 2 to the power n. So you can see over here, absolute value of an is summation 1 by 2 to the power n, and summation 1 by 2 to the power n, that is the geometric series 1 by 2 to the power n, right? Because an equal to 1 and r equal to ratio 1 by 2. Because r equal to ratio 1 by 2 is less than 1 by geometric series test, this series is convergent. But which series is convergent? Absolute series is convergent. Absolute series is convergent. Absolute, I just took the absolute value. Absolute series is convergent. Right? Absolute series is convergent. So absolute value of my series is convergent. Now, I would like to take this is the absolute series test. One more thing you are going to learn in your 301 course, advanced math course, that is absolute convergence implies ordinary convergence, but ordinary convergence does not imply absolute convergence. But right now I think, no, we are not concerned about that thing. I gave you the hint. But right now, I would say that whenever you have alternating series, negative 1 to the power n, 1 by 2 to the power n. So write down this alternating series in different several terms, at least 5-7 terms. So if I take n equal to suppose 0, so negative 1 to the 1 by 2 to the power 0 is simply 1. If I take n equal to 1, negative 1 by 2. n equal to 2, so negative 1 by 2 square, negative 1 square is 1, and 1 by 2 square is 1 over 2 square. Minus 1 over 2 cube, plus 1 over 2 to the power 4, minus 1 over 2 to the power 5. So you can see my terms are positive, negative, positive, negative, positive, negative, positive, negative, means terms are alternating. Terms are alternating. That is the first condition for the Leibniz test here, that your terms are alternating. Look at over here, terms are alternating. And second condition is each term, look at my arrow, each term is numeric. Now I don't pay attention about the signs because terms are alternating. I'm done with the signs. Now it says that each term, that means I'm just counting this term without plus or minus. Each term is numerically less than the preceding term. So 1 by 2 is less than 1, 1 by 4 is less than 1 by 2, 1 by 8 is less than 1 by 4, and so on. So each term is numerically less than the preceding term. And my third condition, n term tends to 0. So if I take the nth term, so limit n tends to infinity of an, irrespective of your sign, just take the positive sign, 1 by 2, limit n tends to infinity, 1 by 2 to the power infinity. So 1 over 2 to the power infinity, 1 over infinity is 0. So n term tends to 0. If these three conditions are satisfied without applying anything, we'll say that by Leibniz test, your series is convergent. By Leibniz test, your series is convergent. So three conditions are there. Your terms are alternating, alternatively positive and negative, and so on. Each term is numerically less than the preceding term, and nth term tends to 0. Nth term of the series tends to 0. Whenever you have these three conditions satisfied, their series is called convergent. And this is the example. The series is convergent. This is the example. We have plenty of examples. Look at over here. One more example. Suppose I take 1 over n and n plus 1. Look at over here, guys. 1 over n and n plus 1. You have product of two functions in the denominator. So without thinking about anything, just first try to go for the method of partial fraction. So I take 1 over n and 1 over n minus 1, right? You know how to use method of partial fractions. I don't want to repeat the same thing. We did this thing last week. So partial fraction will give you, take a over n and b over n plus 1. So you're going to get a equal to 1, b equal to -1, plug the value. So this is your a and b. Then apply n equal to 1, 2, go for partial sum. So first sum of first n terms. So n equal to 1, 1. And here it is 1 by 2. N equal to 2, 1 by 2 and 1 by 3. And then after, if you open the bracket, all your terms will get cancelled out and you're going to get only first and last term. So 1 minus 1 over n plus 1. 1 minus 1 over n plus 1. And limit n tends to infinity of Sn. If you pass the limit, that is equal to 1. So series is convergent, right? Series is convergent. Why I took this example over here at this stage? I think Leibniz test is only over here. This is just one separate example, right? One separate example. Okay. Yeah, different examples. Now see, okay. So now I'm going to, my Leibniz test is over here. I took the example. You can take number of examples over here. Suppose -1 over 4 to the power 3 or 4 to the power n, right? Something like that. You can take plenty of examples over here. Okay. This is the example of the partial sum. We already went through this one. One more example. Limit 2 tends to infinity n over. Now I am collecting several types of examples and I'm letting you know this thing, that which test is appropriate for the given example. Suppose I take limit n equal to 2 to infinity n over ln of n. Why I started with 2? Why not 1? Usually we start with 1, but right now I just start with 2 because ln 1 is 0, not defined. ln 1 is 0. And if you take n equal to 1, so 1 over 0 is infinity. So your series, your function is not defined. And that's why here you have to make sure, first of all, your domain. Your function must be well defined in the prescribed domain. So n equal to 2, if you take ln 2 is some number 0.03010, something like that, right? But it is not 0. So n equal to n over ln n, n over ln n, right guys? If I pass the limit n tends to infinity n over ln n. Now if I apply n tends to infinity, this is infinity over infinity, indeterminate form. Indeterminate form. Let me take this one here. Okay, indeterminate form. That means I can take the individual derivative. Derivative of n is 1, ln is 1 over n, so it is n. If you pass the limit, it is infinity, divergent. Divergent, right? So why I did this thing? Because for this particular series, I am using nth term, negative of nth term test, negative of nth term test, negation of nth term test. That my nth term, I just took the nth term, I apply my indeterminate form, and I say that my nth term does not tend to 0, so it is infinity. Nth term does not tend to 0. That means by negation of nth term test, series is divergent. Look at here. So you are the right person to fix this one, that which test is applicable over here. N over n plus 1 will not give you anything. But if you think about the nth term test, negation of nth term test, yes, it is there. One more example for Leibniz test, -1 to the power n plus 1 and 1 over n. If you take n equal to suppose 1, 1 means 1 plus 1 is 2, -1 square is 1 and 1 by 2. Sorry, 1 by 1 is 1. N equal to 2, 2 plus 1 is 3, -1 cube is -1, 1 by 2. So 1 by -1 by 2, plus 1 by 3, 1 by 4. Terms are alternating. Forget everything. Leibniz test. Leibniz test, terms are all alternative. First condition satisfied. Each term is numerically less than the preceding term. 1 by 2 is less than 1. 1 by 3 is less than 1 by 2. 1 by 4 is less than 1 by 3 and so on. Third term. Limit n tends to infinity of 1 over nth term, 1 over n. Because 2, 3, 4 up to n. So 1 over n. And that tends to 0. That tends to 0. So all three conditions are satisfied. So you need to mention this thing by Leibniz test, or you can write Leibniz test over here. By Leibniz test, summation of an is convergent. Summation of an is convergent. You are going to get the example like this in your final, maybe internal too. This type of example, example number 6. Yes, you are going to get this type of example. Just pay attention, guys. Example 6. Whenever you have 2n plus 3, 3n plus 5, something like this at that time, or 3n square, 2n square plus 5, right? Most likely, whenever your power of numerator and denominator are same, just a hint, not always, right? Just think about the nth term test. This is the hint I'm providing you, right? This is not the rule. Because if you take the nth term over here, 2n plus 4 and 3n plus 1, if you pull this n out, you're going to get 2 plus 3 by n. You want me to solve this example for you guys on whiteboard? Yes or no?
Yes, please.
Sure, that'd be
Okay.
great.
Okay, write down both of these examples in a separate piece of paper. All of you, I give you 1 minute. Both of these examples, please write down in a separate piece of paper. I'll be back soon in 1 minute. Charge my computer. Okay, guys, let's continue. So let me start with my whiteboard. Just give me these 2 examples. 2n plus 3, 3n plus 5. Okay. So it is summation of yes, please, guys. 2n plus 3
Over 3n plus 5.
n plus 5 n runs from 1 to infinity, right?
Yes, sir.
Okay. Now, guys, whenever you have this type of example, always try to think about the nth term test. nth term test. Nth term test says that first of all, yes, if an does not tend to 0 as n tends to infinity, means summation of an is always divergent, right? This is the negation of nth term test. This is the nth term, or you can say negation of nth term test. So here my an equal to, so limit n tends to infinity of an, that is equal to limit n tends to infinity of 2n plus 3 divided by 3n plus 5, 3n plus 5, that is equal to limit n tends to infinity n common 2 plus 3 over n divided by n common 3 plus 5 divided by n, and n will get cancelled out. If you apply n tends to infinity, 3 over infinity is 0, 5 over infinity is 0, you're going to get 2 by 3, and 2 by 3 is not equal to 0. Agree? 2 by 3
Yes,
is
sir.
not equal to 0. And hence, you need to mention like this. You don't have to write over here n term. If you want to write n term test, that sounds good. I will count this one. Otherwise, you have to mention separately over here. Hence, by negation of nth term test, by negation of nth term test, summation of an is divergent. Summation of an is divergent. Does it make sense? Yes or no, guys? Same.
Yes, sir.
That makes
What
sense.
was the second example? What was the second example?
3n squared over 2n squared plus 1.
3n square over 2n square plus 1?
Yes, sir.
Sure.
Yes, sir.
Was it like this?
Sir, that's it.
All of you?
That's it, sir.
Okay. Usually I give some number over here too. But if it is 3n square, that's fine. Usually you may get 3n square plus 5, something like that. But if it is just 3n square, same thing. So my an will be, so an equal to, let me take n square common. So 3 inside. Here if I take n square common, 2 plus 1 over n square. And then limit n tends to infinity. Limit n tends to infinity. So that is my nth term. This n square and n square will get cancelled out. And if you pass the limit as n tends to infinity, you're going to get 3. And here it is 2 plus 1 over infinity is 0. So that is equal to 3 by 2. And 3 by 2 is not equal to 0. So by n term test, summation of n is divergent. Make sense? Summation of n is divergent. Is it okay, guys?
Yes, sir.
Any doubt? Any doubt? Okay, good. So, shall I stop sharing this screen whiteboard?
Yes, sir.
Rachel, are you still writing?
No, sir, I just finished.
Okay. Alexis? Alexis. Okay. So now let's again continue. So all my test and everything, I think that is done about the infinite series. And now we are going to see the last article of our syllabus. That is the Taylor's and Maclaurin's polynomial. Taylor's and Maclaurin's polynomial. Please keep in mind this thing, guys. Taylor polynomial, that is the expansion of function in 2 dimensions like this. Expansion of function at some point over here, here, here. Look at my cursor. Here, 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 here. It could be anything. But if I take this expansion of function, if I take this x equal to instead of c, if I take this point over here at 0, that is called the Maclaurin series. That is the Maclaurin series. So Taylor series expansion is the expansion of function anywhere over here in the plane. In this expansion of the function that is given by Pnx, that is the polynomial, Taylor's polynomial, f be a function whose first n derivatives exist at x equal to a. If you fix one point, x equal to actually c. X equal to c, one point c or a, whatever it may be, any real number. So your derivative of all terms derivative, nth term derivative, 1, 2, 3, 4, first, second, third, suppose fx equal to sine x, fx equal to e to the power 2x, right? You can go up to nth derivative. So this nth derivative exists at this point, If that is possible, then Taylor series of degree n. Why degree n? Because we are writing up to nth term. Look at here. Look at over here, 1, 2, 3, up to n. So f of a plus x minus a, f dash a plus x minus a square by 2 factorial f double dash a, or you can write, here it has to be c. This is not a. This is a printing mistake. Once you have c over here, it has to be c over here. Here c, c. Otherwise everywhere a. F of a, x minus a, that is this point, x equal to a or c, you can say, but not a and c. A and c both are same here. Please guys, this printing mistake, please make sure. X minus c square by 2 factorial f double dash c, x minus c cube by 3 factorial f triple dash c, and so on, x minus c to the power n by n factorial f to the power n of c. N of c. Here, if I take suppose c equal to 0, c equal to 0 means your first term is 0, f of 0. C is equal to 0, x times f dash 0, x square by 2 factorial f double dash 0, x cube by 3 factorial f triple dash 0, and so on. Let me take the first example. I think both of these series, Taylor series, Taylor polynomial and Maclaurin's polynomial, both of these polynomials expansion that is given in your formula sheet. What is the advantage? Advantage means, see, you can write one function. Suppose I give you one function fx equal to x e to the power x, exponential function. Right? So you can write this exponential function in the series expansion form using the Taylor series and the Maclaurin series. Series expansion form. So every function can be expanded in terms of a series form, infinite series form by Taylor series if you are working with a function of one variable. You are going to see the Taylor series in your Calc 3 course for the function of two variables in your partial derivatives. Right? Just keep in mind this thing. We are the least concerned about it in Calc 2, but in Calc 3 you are going to learn this thing. Good. So this is just a function of one variable, function of two variables. That means just keep in mind this thing, the Taylor series is applicable to function of 1, 2, 3, 4 variables too. Right? But right now, just function of one variable. Function of one variable. Suppose I take e to the power x, the expansion of a function about some point, suppose x equal to 0 here. It could be a, some other point, x equal to 1, x equal to 5, x equal to 1.2, 3 by 2, 4 by 7, whatever it may be. It could be any point, but right now, just for the sake of convenience, I would like to start with the Maclaurin series. Means expansion of function about the origin, or about the origin. If I write fx equal to e to the power x, how many derivatives I'm looking for? 1, 2, 3, look at here. First derivative, second derivative, third derivative, nth derivative. So go up to nth derivative of this function. So I just go for nth derivative, e to the power x. I don't write this one first. I just write my left side. Fx equal to e to the power x. Second, third, fourth derivative will remain the same because exponential function, if it is negative, then e to the power x and negative 1. So negative e to the power negative x. Right? So please make sure about the derivative. You know the derivative, guys. Don't ask me. Then after we are expanding the function about x equal to 0. So whatever x you have, replace your x by 0 throughout. So x equal to 0 e to the power 0 is 1. X equal to 0 e to the power 0 is 1. X equal to 0 e to the power 0 is 1. Means all my derivatives are 1 for this particular example, exponential function. All my e to the power 0 is 1. Just go back and plug the values over here. F of 0 is 1. So here it is 1. X, f dash 0 is 1. So x square by 2 factorial, f triple double dash 0 is 1. X cube by 3 factorial, f triple dash 0 is 1, and so on. That means e to the power x is expanded using the Maclaurin series, or exponential function e to the power x expansion about the point x equal to 0 origin is nothing but 1 plus x square by 2 factorial plus x cube by 3 factorial x to the power 4 by 4 factorial dot x to the power n by n factorial. That means every function can be expanded in terms of the infinite series. That's what Taylor and Maclaurin's Taylor says, mainly Taylor. Every function can be expanded in terms of infinite series. Okay, just for your knowledge, it is not in your syllabus, but just for your knowledge and not in any of your books too. Actually, I wrote it down here equality, but that is not exactly equal. It's a small, minute difference is there in terms of some decimals. So every function can be approximated. Actually, it should be, the symbol should be like this. Look at my cursor. It should be like this. Like this. That is the symbol of approximation. Every function can be approximated by the infinite series. Now, this was, I think, identified in 17th century. Then after, people were well worried about the converse part. Is it possible that you have some infinite series and that infinite series will go to some function? Means you can approximate that infinite series by a function. Is it possible? And that question remains remained almost unsolved for, I would say, 3 to 4 decades. And then after one of the mathematicians, I think German or French, German mathematician, his name was Weierstrass, Weierstrass, Weierstrass. He figured it out, this thing, yeah, converse is also true. That if you have some convergent infinite series, that would be approximated by some function. So converse is also true. Because the converse is true, and that's why I used over here the equality sign. But actually equality sign is not good. Actually it's an approximation sign. Because the function is approximated by the infinite series, and the converse infinite series can also be approximated by a function. Are you getting me, guys?
Yes, sir.
Sir, so is that example in the box, that's the Maclaurin
That's the
series?
answer. That's the answer.
Right?
Yeah.
That the function is approximated by the infinite series using this Maclaurin's polynomial. That's it. So just take the derivatives, plug the values in the formula, you're done. Simple. Weird part.
Yes, sir.
Are you getting me?
Yep.
Good. Any other question, guys? Any other question?
No, sir.
Okay, Davis Alex says she goes just out of the room very frequently. Okay, second example, suppose sin x. So fx equal to sin x at x equal to 0 again, Maclaurin series. X equal to 0 means Maclaurin series. So fx sin x, cosine x, negative sin x, negative cosine x, make sure about the derivatives, and then replace x by 0 throughout. So f of 0 is 0, f dash 0 is 1, f double dash 0 is 0, negative 1, and so on. Plug all these values. Then you are going to get sin x expansion is, sin x function expansion is about 0 is x minus x cubed by 3 factorial plus x to the power 5 by 5 factorial minus x to the power 7 by 7 factorial, and so on. These are very standard expansions. In future, you are going to use this sin x equal to this one, e to the power x equal to this one. It is to be understood that it comes through the Talor series or Maclaurin series. It's very standard expansion. Thanks to Talor, big contribution. Yeah. Same way cosine, no, sorry, my bad. Same way cosine x. So cosine x, again, sin x is replaced by cosine x, derivative is negative sin x, then negative cosine x, then sin x, blah, blah, blah. Replace x by 0, same thing. So cosine x expansion, because cosine 0 is 1. You know sin x, why sin x doesn't start with 1 and sin x starts with x? What's the graph of sine function? Sine function graph starts with 1. Do you remember that thing? Yes or no?
Yes, sir.
It does not touch the intersection of your graph, 0. Sine function does not touch 0. If you look at the graph of sine function. But cosine function graph starts from 0. So cosine 0 is 1. Because cosine 0 is 1, your first term is 1. But sine 0 is not 1. Are you getting me? Right? Sine 0 is 0. And that's why we don't write it, C0. But cosine 0 is 1. So that's why your expansion starts with 1. So 1 minus x squared by 2 factorial x to the power 4 by 4 factorial and so on. For sine function, you have all odd powers and factorials, all even powers and factorials. Just to keep in mind this thing, otherwise it's not that important for you guys at this level. Okay, my next example. Fx equal to sin x. Now, I said that don't go up to n terms, but go up to n equal to just 5 terms. First 5 terms, right? The expansion of first 5 terms. Not the Maclaurin series. Go for the Talor series. See, c equal to pi by 6 now. C equal to some point, pi by 6. I don't want now 0. I want to expand my function sin x till 5th term about the point c equal to pi over 6. So first of all, I can start by fx equal to sin x, f dash x cosine, negative sine, 5th term, so I have to stop over here. F 5th of x equal to cosine x. Replace your x by pi over 6. So f pi over 6, sine pi over 6 is 1 by 2. Cosine pi over 6 is root 3 by 2. Negative 1 by 2, negative root 3 by 2, and so on, up to here. Plug these values in your Talor series polynomial. Your Talor series polynomial was this one. This is your Talor series, f of c equal to pi by 6, so f of pi by 6. x minus pi by 6, f dash of pi by 6, x minus pi by 6 square by 2 factorial, f double dash of pi by 6, x minus pi by 6 cube by 3 factorial, f triple dash of pi by 6, and so up to fifth terms. So x minus c to the power 4 by 4 factorial, f to the power 4 of pi by 6, x minus c to the power c is pi by 6, x minus pi by 6 to the power 5 over 5 factorial, f fifth derivative at pi by 6. And you have to stop that. And you have to stop that. Look at here. And then plug the values. I just plug the values. So f at pi by 6 is 1 by 2. F at pi by 6 is 1 by 2. X minus pi by 6. F dash at pi by 6 is 3 by 2. Blah, blah, blah. And then just simplify this one. I just took this negative sign out. Or you can leave it over here. I don't mind. If everything is right up to here, I will give you full points. If you want to go for the simplification, it's okay. Otherwise, I'm good. Because 5 factorial, I just wrote it down. 4 factorial is, what is 4 factorial? 24. 24 multiplied by 2 is 48. 5 factorial is 120. 120 multiplied by 2 is 240. So it's just a matter of simplification. And I'm done. Thank you.
Oh, sir,
Yes.
I have a quick question about Taylor's polynomials. When we're asked questions about this on the test, are they going to be presented in the same format, or like if you scroll up, will you just give us the function and then the c value and the n value, or
I'm going to ask you like this.
just okay? And you want us?
I'm going to ask you like this. Expand the function fx equal to sine x in terms of Taylor's or Maclaurin's polynomial that you have to decide up to n equal to 5 at the point c equal to pi over 6, like this.
Okay. Thank you, sir.
Just first line you're going to get as your example. If you have c equal to 0, Maclaurin's, otherwise Taylor. Right?
Yes.
So here also, just find the Maclaurin's polynomial of fx equal to the power x about 0. I will not write about 0 here. Here I gave you about 0, but I'm not going to write this one in the exam. Because once I mention Maclaurin's, it is to be understood that expansion of the function about 0. Make sense?
Yes, sir. Thank you.
Good. If I want to stop at 5th step or 8th step or 9th step or 10th step, I will mention n equal to 9, 10, whatever it may be. If nothing is mentioned, go up to nth term. Clear, Achen?
Yes, sir.
Good. Any other question, guys? Any other question?
Sir?
So just wait. Yeah, so I hope you don't have any question, right, guys? If you have any question, you can ask me. If you don't have any question, then let's stop here, because this is the end of the syllabus. Tomorrow morning exam, day after tomorrow review session, Thursday morning, Thursday afternoon, final and done. So we are in time. See, I told you, we are in time, right? I finished everything in time. Everything, including everything. I didn't miss a single part. Yes.